Welcome to Lesson 4 in Linear Algebra. This lesson is about the properties of a vector space, that is, the properties of the arithmetic we've learned about vectors, vector addition, scalar multiplication, and also the vector dot product. Why do we care about properties? Well, we would like to be able to solve equations involving vectors and later vectors and matrices. For example, what can we say about the relationship between the vectors u, v, and w with this equation, or what can we say about those vectors with an equation like this involving not only a addition but dot products. But before we can proceed to solve equations like this, we need to know which operations are valid, which ones will produce real solutions and not false solutions. For example, back in high school algebra, we learned some invalid things to do. It's invalid to multiply or divide both sides of an equation by 0 because we can make any two things equal that way because both sides will come out 0. It's also illegal to extract the square root of a negative number unless, of course, you're dealing with complex numbers. So similarly, as we deal with vector algebra and vector arithmetic, we need to know which properties hold and which things we need to be careful of. So we'll start with the additive properties of vectors. It shouldn't be too hard to see, and we've seen examples of this, that if I add the 0 vector to any vector, I get the vector back. That is, it has no effect, and it doesn't matter which side I add it on. We say that the 0 vector is the additive identity. Now we're going to demonstrate that these things are true, have short proofs, in three-dimensional space generally, but these properties hold in any dimensional space, 2, 3, 4, 5, 50-dimensional space. So let's consider how we show that this property is true in three-dimensional space. We can let u have the elements ABC. Then if I add u plus the three-dimensional 0 vector, that's ABC plus 0, 0, 0, and by the rule for vector addition, this is a plus 0, comma b plus 0, comma c plus 0. But now notice the addition that's happening is real number addition, and we know that works. A plus 0 is a, b plus 0 is b, c plus 0 is c, because now this addition is no longer vector addition, but it's addition of real numbers, and we know how to do that. So indeed we get u, and similarly the other way if we add 0 on the other side. One that's not quite so obvious is that vector addition is commutative. That is, if I add u plus v, I get the same answer as adding v plus u. Again, in any dimensional space. But let's look at the proof in three-dimensional space. I let u have the arbitrary elements a, b, c, v have the elements d, e, f. Then if I literally apply the definition of vector addition, u plus v, that's the vector a, comma b, comma c, plus the vector d, comma e, comma f, that gives me a plus d as the first element, b plus e as the second element, c plus f as the third element. So that's that vector. But now again, the addition of each of these coordinates or each of these elements is real addition. So a plus d is the same as d plus a, and b plus e is the same as e plus b, etc. So this vector is identical to this vector. So now we do something that may be not quite so obvious. I can break this up into two vectors. One vector with the components d, e, f, and the other vector with the components a, b, c. Why? Because this is what the rule for vector addition says. If I take the vector d, e, f and add it to a, b, c, this is precisely what I get. D plus a, e plus b. That is, my definitions of vector addition and scalar multiplication work both ways. Because this is equal to that, then vice versa. This must be equal to that. And this is precisely v plus u, so we've proven in the three-dimensional case that u plus v by this chain of equalities really is v plus u. This has a nice geometric image that we looked at before when we first considered geometric vector addition, it says if I take the vector u and add on the vector v, where that's represented by this purple line, I reach exactly the same point as if I take the vector v first and then add the vector u. So the total vector u plus v along this diagonal is the same whether I add u plus v or v plus u geometrically, because we've shown it's true algebraically. There are some more properties of vector addition. An interesting one is if I add the vector u to the vector negative u, I get the zero vector. That is, minus u is the additive inverse of u. Let's prove this in three-dimensional space. If u has coordinates a, b, and c, I define the negative of a vector as minus 1 times the vector. So negative u has components negative a, negative b, and negative c. Then if I add u and negative u, I'm adding the vector with coordinates a, b, c to the vector with coordinates minus a, minus b, minus c. And by the rule for vector addition, that's a plus negative a, or a minus a, comma b plus negative b, or b minus b, and then c plus negative c, that's c minus c. So a minus a is 0 by the rules of real number arithmetic, b minus b is 0, c minus c is 0, so indeed I get the zero vector. So this means, because a, b, and c weren't specific numbers but arbitrary symbols representing an arbitrary vector, that every vector has an additive inverse, simply minus 1 times that vector. Another very important property to consider is associativity of vector addition. It turns out that associativity is a fundamental property. We need it in order to be able to do almost any arithmetic or algebraic operations. So let's see why, if I add v plus w first and then add u, I get the same thing as if I add u and v first and then get w, add w. So in R3 again, we will define three arbitrary vectors. U will have coordinates a, b, c, v will have coordinates d, e, f, and w will have coordinates r, s, t. Then if I literally follow the rules for vector addition, if I add the vector u to the sum of the vectors v and w, I have to add v and w first. So here's the vector u, a, b, c, and what would be the vector v plus w? It would have elements d plus r, e plus s, f plus t, as listed here. But now I have another vector addition to do, but what does the rule say? It says I can add the first element of the first vector to the first element of the next vector. So we have to consider d plus r as an element and add this way, a plus the quantity d plus r. Similarly, we add b by the rule for vector addition to the quantity e plus s. And finally, we add c to the quantity f plus t. But once again, now we've moved the plus sign from a vector operation to real operation, real number arithmetic. So in the real numbers, a plus the quantity d plus r is the same as the quantity a plus d plus r. Why? Because we know that real number addition is associative. I can move the parentheses around freely. Similarly with this second element, b plus the quantity e plus s is the same as the quantity b plus e plus the quantity s, because real number addition is associative. And similarly with the last element, c plus the quantity f plus t is the same as the quantity c plus f plus t. But now, by the rules of vector addition, I can break this result up into two vectors. The vector whose first element is a plus d, whose second element is b plus e, whose third element is c plus f, and the vector with elements r, s, t. Because, by the rules of vector addition, this vector plus that vector gives me the previous result. And then I do it one more time. The vector with elements a plus d, b plus e, c plus f can be broken up into the sum of two vectors. The vector with elements a, b, c, and the vector with elements d, e, f. But that's exactly the quantity u plus v, the vectors u plus v. So I've proven that u plus the sum of the vectors v plus w is the same as first computing the sum of u plus v and then adding w. So vector addition, at least in three-dimensional space, is associative. In fact, it's associative in any dimensional space, any finite dimensional space. Now we have some scalar multiplication properties. It should be easy to see that if I multiply the scalar 1, the real number 1, times any vector, I get that vector back. Another interesting property is that scalar multiplication distributes over scalar addition. So if I multiply the scalar s by the sum of the vectors u plus v, I get the same answer as multiplying the scalar by each of the vectors individually and then adding the scaled vectors. So let's show this in three-dimensional space. Let u have elements a, b, c, v have elements d, e, f, and s be some arbitrary real number. Then by definition, using my parentheses, the first operation I have to do to compute s times u plus v is to add the vectors u and v. Well, what is u plus v? With these definitions, u plus v is the first element is a plus d, the second element is b plus e, the third element is c plus f. And that's what I scale by my scalar s. Now by the rule for scalar multiplication, what do? I take the scalar and multiply it by each element. So I need s times the first element. The first element is, or first coordinate, is s times the quantity a plus d. Similarly, I multiply s by the entire second coordinate, s times the quantity b plus e, and s times the quantity c plus f as the third element. Once again, I've transformed my operations from vector operations to a set of scalar, real number operations. So now I can rely on the distributive property of real number addition and multiplication to produce the new vector. I can distribute the s and get the first coordinate to be sa plus sd. I can distribute the s in the second coordinate and I get sb plus se. I distribute the s in the third coordinate, I get sc plus sf. But now each of these elements or each of these coordinates is a sum, so I can break this up into the sum of two vectors. The first vector with coordinates sa, sb, sc, and the second vector with coordinates sd, se, and sf. And this works because of the rule for vector addition. Finally, I can factor out the scalar s because it's multiplied by each element in both of the vectors. So I get s times the vector abc plus s times the vector def. That's precisely su plus sv. So I've proven, at least in three dimensions, that scalar multiplication distributes over vector addition. Similarly, scalar multiplication distributes over scalar addition. That is, if I add two scalars and then multiply by a single vector, I get the same result as scaling the vector with the first scalar, scaling the vector with the second scalar, and then adding the two vectors. Notice this is pretty unique. Here the addition is scalar addition, s plus r, and on the other side the addition is vector addition, su plus ru. But it works, and you'll prove that as one of your assignments. Finally, this other one is interesting also. Scalar multiplication is compatible with real multiplication. If I first scale a vector by r and compute the vector ru, then I scale that vector by s, so s times the scaled vector ru, I get exactly the same answer as if I multiply the scalars first. Here the multiplication is scalar, is the multiplication of real numbers, not scalar times vector. So I multiply s times r and then take that product and multiply it by u. I get the same answer. This set of properties really helps us to see what operations we can do when we're doing vector arithmetic and vector algebra. Finally, we'll consider some Properties of the vector dot product. First, the vector dot product is commutative. U dot v is the same as v dot u. That shouldn't be too hard to think about. Why? Well, it's just the vector dot product is the sum of the products of the corresponding elements, and each of those products is a real number product, right? Product of two scalars, so that commutes. Well, you'll have a chance to prove that later. The vector dot product distributes over vector addition. This is an important and not so obvious property. If I add the vectors v plus w and then compute the dot product, u dotted with that sum, I get the same answer as if I do u dot v and then u dot w, and those are real numbers, right? That's u dot v is a real number and u dot w is a real number. If I add those two real numbers, I get the same result. So here again, the addition on the left-hand side is the addition of vectors. The addition on the right-hand side is the addition of real numbers because I'm computing the dot products first. But it works, and let's see why it works in three-dimensional case. So I let u have the elements a, b, c, v have the elements d, e, f, and w have the elements r, s, t. Then what do we have? We start with the left-hand side. I compute u dot v plus w. Well, I have to add the vectors v plus w first. That's d plus r, e plus s, f plus t. So there's v plus w, and I take the dot product of a, b, c with that vector. So now I apply the rule for the vector dot product. What do? I multiply a times the first element here, multiply a times the quantity d plus r, and then multiply b times e plus s, multiply c times f plus t, and I add those up. So now I'm out of the vector world again. This is just an expression using real number arithmetic. So I have my distributive property of real arithmetic, that multiplication distributes over addition. So this first piece of this expression is actually AD plus AR. The second piece is BE plus BS. The third component is CF plus CT. Now, real arithmetic is commutative and associative, so I can change the order of these elements freely, and I can move the parentheses around freely. So I'm going to collect the pieces that have DEF in them. So I have AD plus BE plus CF. I'm going to collect that as one of my terms, and then I have AR, BS, CT. This is legal because scalar addition or real addition and multiplication are both commutative, and the addition and multiplication actually are associative. But what is this? AD plus BE plus CF, that's precisely the vector dot product of U dot V, that is ABC dotted with DEF. And what's this quantity? AR plus BS plus CT. It's precisely the dot product of ABC, the vector with elements ABC, with the vector with elements RST. So the result is U dot V, that number, plus the number U dot W, and that proves that the vector dot product distributes over vector addition, at least in the three-dimensional case. A couple of more interesting vector dot product properties. If I multiply a scalar times a dot product, U dot V, I can actually multiply that scalar anywhere. In other words, I can multiply the scalar after taking the dot product, or I can multiply the scalar times the first vector and then take the dot product, or I can multiply the scalar times the second vector and then take the dot product. I can move that scalar freely around, and that's useful especially when dealing with unit vectors. And finally, if I take the dot product of any vector with the zero vector, I get the real number 0. And the proof is very simple, as listed here. I let U be ABC, then U dotted with the 0 vector is ABC dotted with 0, 0, 0, which is A times 0 plus B times 0 plus C times 0. And of course that's 0. Okay, so here's a couple of examples of using the properties of vector arithmetic. I want to simplify this expression, 3 times the vector sum u plus v plus the vector sum 4v minus 2u. Well, what can I do? I can use my fact that scalar multiplication distributes over vector addition in the first step. So 3 times u plus v is the same as 3u plus 3v, and I've left the second expression alone. Vector addition is commutative. We proved that, at least in the three-dimensional case, so I can swap the order of the addition here. 4v minus 2u is the same as minus 2u plus 4v. And now, because vector addition is associative, I can move the parentheses around. That is, I can decide to compute 3v minus 2u first, and then compute 3u plus the quantity, 3v minus 2u, and then finally add 4v. Once more, I can apply the fact that vector addition is commutative. So 3v minus 2u is the same as 2u minus 3v. I can apply the associative property one more time and group the first two elements together and get 3u minus 2u, and group the second elements together and get 3v plus 4v. Now I can apply the fact that scalar multiplication or scalar addition distributes over scalar multiplication to factor out the u from this expression. So 3u minus 2u is the same as 3 minus 2 times u, and 3v plus 4v is the same as 3 plus 4 times v, and that reduces to 3 minus 2 is 1, so I get u, and 3 plus 4 is 7, so u plus 7v. And the only reason I could actually do this process, the only way I could simplify this vector expression, was to know which properties apply, that vector addition is associative, commutative, and I have my distributive properties. Another example, we can solve the vector equation 4 times u plus the vector 4, 1, 8 equals a different vector 2, minus 3, 5 for the vector u using my properties of scalar arithmetic. For example, I can subtract the vector 4, 1, 8 from both sides by substitution of equal things. So the quantity 4u plus the vector 4, 1, 8, if I take that quantity and subtract 4, 1, 8, that's the same as taking the other side, 2 minus 3, 5, and subtracting 4, 1, 8. So if I do the vector arithmetic on this side, that's 2 minus 4 is negative 2, minus 3 minus 1 is minus 4, and 5 minus 8 is minus 3. If I use the fact that vector addition is associative, I can group the 418 minus 418 together, and that clearly gives me the 0 vector. And 4u plus the 0 vector is just 4u. So now I've reduced it to 4 times u is this single vector with elements minus 2, minus 4, minus 3. Finally, I can solve for u by multiplying both sides of the equation by 1/4. Or equivalently, we could say that that's substituting equal quantities. I know that the quantity for u is the same as the quantity, excuse me, that little mix-up. The quantity for u is exactly the same as the quantity minus 2, minus 4, 3. And so now I'm multiplying 1/4 by the same thing on both sides. But what's 1/4 times 1/4 times 4? It's 1. So I have 1u or u on the left side. And what's 1/4 times this vector? I can distribute the 1/4. It's scalar times vector. So I get elements minus 1/2, minus 1, and minus 3/4. Okay, so that's a couple of examples of how we use the properties of vector arithmetic to solve equations or simplify expressions. Now it's your turn. So your first task is to, without knowing the particular size of these vectors or their elements, just using the properties of vector arithmetic, simplify the expression 4 times the vector u minus the vector v plus 3 times the vector v minus the vector u, and show each step and list the particular vector properties you use to accomplish that step. The second one is to prove that if I take the dot product of u with the vector quantity v minus w and then add the following dot products, w dot u minus the dot product v dot u, I get 0, and justify each step. So pause the video here, work these exercises to the best of your ability, and then we can compare answers. Okay, I hope you were successful in working these exercises. Let's see if we can compare answers. Well, how do I simplify this expression? I use the properties. I use the fact that scalar multiplication distributes over vector addition. So I get that 4 times u minus v is 4u minus 4v, and 3 times v minus u is 3v minus 3u. And then vector addition is commutative and associative, so I can regroup freely. I can put the v's together and the u's together. So I have 4u minus 3u and 3v and negative 4v. Again, because I can reorder the terms, because scalar vector addition is commutative, and I can regroup them because it's associative. I can use the scalar addition distributing over scalar multiplication and factor out essentially the u out of the first expression. So 4 minus 3u and then 3 minus 4v are the results. And that's, of course, 4 minus 3 is 1, so I have 1u or u, and 3 minus 4 is minus 1, so this simplifies to u minus v. Okay, and then finally, for the second problem, I want to prove that u dot the vector difference v minus w plus the sum of the two dot products v dot u minus v dot w dot u minus v dot u gives me 0. So what do I do first? I can distribute the dot product over the vector addition, so this becomes u dot v minus u dot w, and then this remains the same. And now vector addition is commutative and associative, so I can regroup my vectors. I can take u dot v and subtract v dot u, grouping those two together, and then I can group w dot u minus u dot w. But we also know that the vector dot product is commutative, so I get u dot v minus minus u dot v and u dot w minus u dot w. Now it should be clear that that's 0 because I'm subtracting two real numbers that are equal, but we can prove it by factoring out the v in the first expression, so I get u dot v minus v, that's u dot 0, and u dot w minus w, that's u dot 0, and both of those we proved give 0, so indeed the whole expression gives me the real number 0. Okay, well, hopefully you found this exercise useful in seeing how we can prove vector properties and also how we can use them to do vector algebra. So for homework, please download and study the notes for Lesson 4, Vector Space Properties. That will be posted to D2L, and on Monday we'll get significant practice with using vector space properties to do vector algebra.